Hi, my name is Matt, and this task focuses on solution for L1P task, which involves grasp paths Miss Marple, which is finding the shortest path using the algorithm. Now, in part A, we're trying to find the highest number of the shortest paths from the train station to the hotel where Miss Marple stays, and the graph has the edge west of one. So the best way to solve this is the BFS, as it guarantees the shortest path. So we maintain a distance v, which stores the distance from S to V. In count v, which stores the number of the shortest path from S to V. And we initialize the distance S equals to 0 and count S equals to 1. For all other distance V equals to infinity and the count V equals to 0. So while performing BFS or exploring the neighbors, we find the shorter path, date its distance and copy the path and add it to the count. But if an alternative or another shorter path is found, we add it to the count. So this pseudocode explore this concept in here. The algorithm runs in time complexity of O n plus m, where n stands for the node and m is for the edges. In part B, we are given an undirected graph and we are asked if the graph is connected. So we use the DFS search method where we recurse from a certain node and we check if all the nodes are reachable or visited. If all the nodes are visited, that means the graph is connected. So this pseudocode explores the concept of that. So the time complexity also states of n times, which meets all the requirements. In part C, we consider the same DFS, but this time using the adjacency matrix. Adjacency matrix, we have to check every possible numbers, which takes O of n time per node. So overall, DFS will run on O of n squared, which is slower than adjacency list, but sometimes acceptable for small graphs. Now in part D, we are given a directed graph in the form of a cost adjacency matrix, so we use the Dijkstra's algorithm starting from node 1, and we label it as A. So using a priority queue, we always select the unvisited node with the smallest unknown distance from the source. Then we update the distance to its neighbors. If we find the shortest path, the process continues until all the nodes have been processed. Now the order of the removal from the priority queue is A to B, and then H, D, F, G, C, E, and J, where I is not reachable. So the time complexity for Dijkstra's algorithm using a priority queue is O of n plus m log of n, which is efficient for sparse graphs. So in part we are asked if each edge in a graph that has increased by a constant p, does the shortest path change? So the answer is no, because if you have the p and q, where p is originally the shortest path, then if you change it by a constant k, that only changes the final value but does not change the overall shortest path. Thank you.